All right, so the homework assignment that you're going to be starting on today is due on Thursday. There's a quick turnaround on that. So I've given you some key ideas on the next slide that I think it's a relatively straightforward assignment to begin with. Only, if I'm not mistaken, only one or two of those problems has any calculations. The rest of it is kind of like draw a sketch or do some thinking kind of stuff. So I don't think it's too bad. But maybe what is kind of bad is the project report due a week from today. I guess it could. How bad could it be? Because you've already done a draft submission of your demand estimation, of your pipe sizing. You've done your draft submission of the reservoir. Of course, I haven't given you comments back on that, but I'm going to. I'm going to like ignore my kids tonight and try and get started on those. Daddy, Daddy, get away! You know. So I'll just like ignore my family and work on your reservoir sizing tonight. So there's some real gems out there on the internet. I'd get fired if somebody went through it. All right. Luckily, nobody does. The people who do are in Pakistan and Bangladesh and stuff like that. All right. So the homework assignment is due Thursday. Then you've got the design project due on Tuesday. Now, if you printed out the notes from last semester, you may notice that there's like a bunch of financial calculations related to find what are the quarterly payments and so on. And that's not actually in your assignment description this year. And so the only cost that you have to find out is the present value, or in other words, what's the initial construction cost. So in the past, I had students look up bond rates and find out what would be like the financing alternatives if they did it over 15, 20, 30 years and so on. But that's not in your scope of work. So be sure and read it carefully. I think that the assignment description has everything I expect to see in the report, and I look forward to it. Any quick questions about the project before we get into gradually varied flow? I encourage you to submit written calculations on engineering paper. I think it's really awkward to have typed calculations. Like, it takes so much extra work to type calculations and make them look good. And so I expect you to do a written report where you're explaining your methodology and your assumptions. That should all be typed. But then you can refer to an appendix of handwritten calculations that show, for instance, all of your demand estimation and things like that. Yeah. Well, the fewer files, the better. And I think that it is possible for you to merge it all into a single PDF, but I won't insist on it. And for instance, if you've made changes to your reservoir sizing after I get comments to you, then submit that spreadsheet electronically, as well as if you include a PDF of it in the appendix. Other questions? Okay. So here are some of the key ideas for the homework assignment. Problem 2, I just thought was a little confusing, maybe, the way that it's worded. And so what they're asking for you to find is the DYDL. And we'll go over today what that is. Problem 3 is closely related to an example we're going to be working in class today. But just to make it perfectly explicit, they're wanting to find out how does the water change relative to horizontal. And so what that means is that you have to find DYDL and then subtract out the channel slope from that. Now, in problem 4, they're asking you to classify a water surface profile type. And we'll talk about what those abbreviations mean as we look at some pictures in class today of what causes gradually varying flow. And so what they're asking you to classify is there are these typical shape designations that are assigned. And so they want to know that in Part A. And then in Part C, they want to, based on Part A, they want you to say, is the critical depth upstream or downstream? Is the normal depth upstream or downstream? You know, sort of like what's at the bounds of the gradually variation, because gradually varying flow doesn't vary forever. It eventually matches up with some sort of uniform flow, and so it's asking, you know, where are the controlling depths, and you know which one is upstream and which one is downstream. And then one assumption that you need to make in order to do problem 25 is the coefficient of contraction. And so that's an underflow gate problem where you should use a coefficient of contraction of 0.6. All right. So if you didn't get all those written down, it'll be in the video. We have to keep moving. Let's talk about gradually varying flow. Now, I've got a picture of a river here, and most of the time, the flow will be varying in some way. When we talk about a natural channel, it would be very unusual for us to have any length of channel that is uniform flow unless it's an engineered channel, you know, like a canal that's prismatic with the uniform slope. But far more commonly, we have creeks that are changing their profile, they have variation in slopes, there are obstacles in the way, and all of those things affect changes in the velocity, in the depth, the channel width. Here in this picture, you can see that the width is narrow at one section, it's wide at another. And so over the coming couple of weeks, what we're going to be doing is looking at the numerical methods you need to find out what is the depth and what is the velocity, what is the water slope, when you have these real-world changes in channel width and depth and slope and so on. So there's lots of things that can cause these irregularities, but by gradually varying flow, what we mean is anything other than a hydraulic jump or water flowing over the edge of a waterfall. You know, those are the two instances where the depth of flow is varying rapidly. So rapidly varying flow, RVF, is the hydraulic jump where it's increasing its depth really quickly. Or if water is approaching a drop-off, then it decreases really rapidly. When the depth changes, the velocity does as well to maintain continuity relationship. Now in the calculations we're going to do, we'll assume the hydrostatic pressure distribution as we go down through the depth of the water. And since the water is open to the atmosphere and is moving relatively slowly in open channels, that's an okay assumption for us to make. It's not so bad. And we are going to be accounting for energy loss, whereas in the Bellinger momentum equation, that doesn't account for energy loss. Remember, one of the assumptions in the Bellinger momentum equation was that there's a uniform velocity distribution upstream and downstream. And so the gradually varying flow approaches that we're going to work through kind of do account for the energy loss. So let's look at some pictures. Here is gradually varying flow as water approaches a choke of an underflow gate. And the reason why the depth is increasing is so that enough energy can accumulate upstream of the gate to force the water under the gate at a high velocity. It's looking for in to equal out. And initially, when that gate is dropped, there isn't enough energy to push the water under that gate at a high velocity. And so it begins to pool until finally there is enough energy upstream of the gate so that in equals out and it comes into equilibrium. But this section GVF is the gradually varying flow. Any guesses on what UF stands for? Lots of good guesses. You're right. Uniform flow. All right, so here is water that's approaching a drop-off, and you can see that they've designated that last couple of feet of rapidly varying flow, but it varies gradually as the drawdown occurs as it gets closer and closer to that edge. Another possible cause, probably the most common cause, would just be a change in slope. Now here you can see we have a relatively steeper slope matching up with a relatively less steep slope. And so somewhere there's going to be a gradual variation as the two different normal depths have to match. So here's the normal depth for slope 1, the normal depth for slope 2, and you have to kind of connect the dots between those two depths, and it's going to vary gradually. Sometimes the change in depth will be majority after the transition. Sometimes it'll be mostly before the transition. And we'll learn how to do those calculations later on. Here's another case of gradually varying flow after the underflow gate. In this case, there's no hydraulic jump. And so what that means is that either this is a steep slope or the gate is open enough that it wasn't causing pooling upstream. But I guess the fact that this is gradually varying argues against that. This is probably a steep slope. So those are some causes of gradually varying flow. Now, the equations that we're going to look at today, the main one's called the process equation, which is, I'm not sure how or why it got that name, but it's pretty serious, the process equation. We're going to be assuming that we have a prismatic channel, which hopefully you remember a prismatic channel is one that can be mirrored along a center line. And so it could be U-shaped, and here's the mirror, or it could be rectangular, it could be trapezoidal or V-shaped, whatever shape, but this normal natural channel would not be prismatic. And so the further we get away from a non-prismatic channel, the worse these equations are at predicting what's actually going to happen. And so sometimes what we have to do is break the channel into sections that themselves are prismatic. And then when we do that, then we can kind of get good results again when we break a non-prismatic channel into segments that are. Now, assumed here is that our bed slopes are relatively small, meaning that we have the channel slope and open channel would very rarely be any greater than 2 or 3%. And as long as we stay below that, then everything's fine. Uniform velocity distribution, this is maybe the biggest weakness in what we're going to be assuming, is that, again, the velocity at the bottom of the channel is the same as the velocity at the top of the channel. And that's primarily where we have errors pop up in predicting what we'll observe in the field versus these equations that we're going to be looking at. And so this error is maximized for shallow slopes, but when you have a relatively deep slope, then the error becomes smaller. Kinetic energy correction factor of equals to 1 means that we're assuming relatively laminar conditions, that the flow isn't turbulent. And no, I'm sorry, the other way around. We assume that the flow is turbulent, not laminar. It was the laminar condition is when we have, for example, in a pipe, when we would have the bullet-shaped velocity distribution is when we would have to have the kinetic energy correction factor of equal to 2. So the kinetic energy correction factor of 1 is saying that our Reynolds number is beyond about 4,000. And that's usually the case, even in a slow-moving stream. Parallel streamlines and hydrostatic pressure distribution, and then we assume that the channel roughness is constant for whatever section we're applying this equation over. That is that you're not going to have a section of concrete with a relatively smooth roughness and then like gravel. You would only be able to apply this over sections where the roughness coefficient is the same. So you'd have to break it up into pieces if it was going to be varying roughness through different sections. Okay, this is a really important drawing, and so we're going to look at this for a couple of minutes and talk about what these variables mean. Okay, I guess the most obvious one to begin with, WS, is water surface. We know that's a free water surface because the little triangle and these ripple marks indicate that it's open to the atmosphere. Now above the water surface, here they've abbreviated it TEL in our book, and that stands for the total energy line, which is the same thing as what we called the energy grade line when we were in fluid mechanics last semester. So the total energy line is this dashed one, and the solid line above it is just for purposes of reference. It's horizontal. It's a horizontal line to show, yeah, from my perspective for a second that didn't look horizontal, but it is. It's horizontal to show how much energy is lost along some length dl. And so H sub f is how much energy is lost, And by the way, when you have uniform conditions, H sub f would equal the slope of the channel multiplied by dl. And so this S naught dl equals HF when you have uniform conditions. But we don't have uniform conditions. And how do we know that this is non-uniform? Anyone? Okay, the slope of the water surface is changing. That's a good way to put it. Go ahead. Very good, yes. So uniform flow, all three slopes would have to be equal to each other. The channel slope would equal the water slope, would equal the energy grade line slope, or the total energy line slope, S sub f. Right, so those three slopes would be equal. So we can see that the water's getting deeper in the direction of flow. How do we know it's getting deeper? Well, over here on the left side is y, our original depth. But then over here, it's y plus dy. And so the water got deeper. So why is the velocity changing? Here there's v and then v plus dv. Does that mean that the velocity is increasing? No. Yeah, the velocity is not increasing, assuming the channel is, the width isn't changing. Here the dv would be negative, because if the water's getting deeper, the velocity would have to be decreasing, assuming a constant width. So here's our velocity head at 1 and 2, upstream and downstream. All right, so we've dug into that a little bit. Just to point out that there is a difference in depth upstream compared to downstream. Yes? No, not necessarily. It may just coincidentally appear that they are. Yeah. Okay, now to give you a bit of background, remember our definition of specific energy. It's that at any location it's going to be the depth and the velocity head. And so starting with the idea of specific energy, and then back from lecture 17, we had the idea introduced that the change in energy with respect to depth is 1 minus the Froude number squared. Now what we're going to do with that is try and predict the slope of the water surface. And what we can do is say, well, the total energy, here in the text it's saying the dH dl, where h is the total head, including the depth, the velocity head, and some distance above vertical datum, so z. So if you have the slope of the energy grade line being the change in energy with respect to position, so that's S sub f, we're just saying the slope of our energy grade line is how much energy is changing with respect to the distance downstream. And then the slope of the channel, S naught, is dz dl. And so it's how much elevation is being lost over this length, just channel elevation. So here's what we can do. We can put this into this relationship and predict dy dl. So that's the change in depth with respect to length. Now we have to be really careful though, because although it looks like the water surface is linear, it's not linear. And so we have to be cautious in applying this dy dl, because it only applies at a single point. It's the slope at one location. And so just to exaggerate, we've got the water's getting deeper here. Okay, so let's say maybe it's approaching some sort of an obstacle, and that's why it's getting deeper. All right, so it's getting deeper like this. So it's not a straight line, it's curved. And so at any point, right here, for example, we could find out what is the slope of the water surface there, but we couldn't simply multiply that slope by some distance, delta L, and then find out what is the depth downstream, because if you project the slope, it's not necessarily going to be the same as the result of that curve. We'll talk more about that in the coming classes. We'll talk about, well, if you can't just directly multiply that by some distance, L, then how do you know what the depth upstream or downstream is going to be? So we have to have some ways of integrating this over a distance. And there are some fun spreadsheet ways of doing it. So start bringing your computer again on Thursday, because we're gonna dig into some of those computerized methods. Okay, so this is the general governing equation that's behind all of those methods, and we're just going to look for different ways to integrate it to find out a depth upstream or downstream. You can also use this to find what is the slope of the water surface at a certain point where you know at that location what's the slope of the energy grade line. Now, a word about the sign of slopes. In the past, like when we were working with Manning's equation, if the slope was 1% slope, we just put into Manning's equation S equals 0.01. And it was already assumed that water flows downhill. And so we didn't bother putting a negative sign for the slope into Manning's equation. But here we have to be a little bit more careful about slopes. The channel slope is going to be downhill. And so you do need to put a negative sign in here if you want to find the water surface slope. Because dy dl could be positive or it could be negative. Because sometimes the water is getting deeper in the direction of flow, and sometimes the water is getting shallower in the direction of flow. Remember these. And so we may be using the process equation to look at a situation where the depth is increasing, and other cases where the depth is decreasing. And so in the homework assignment, you have a question where you need to be sure that when they tell you the slope of the channel, you make that a negative number. And the example we're going to work today will reinforce that necessity. Okay, so where do you get the slope of the energy grade line? We can solve that using Manning's equation. And for a certain channel, we may know at a location, we can go and measure what is the depth using a yardstick or whatever. We can know the depth in the stream. We can know the roughness, the channel geometry. And so the only unknown in Manning's equation will be the slope of the energy grade line. You physically measure the slope of the water surface. The slope of the channel. And then based on knowing the depth, you can find the Froude number. So if you make that substitution, putting the Manning's equation into S sub F, here's what it looks like for SI units and for the British gravitational. And the reason why that's different is, of course, Manning's equation in SI is Q equals A to the 5/3, S to the 1/2, and P to the 2/3. And so that's SI units, but in traditional units, we have to do 1.486 as the units conversion. That is really terrible. 1.486. And so this is rearranging that to solve for the slope of the energy grade line, what you'd get for SI units or for BG units. Now, this is true regardless of whether the channel is rectangular or trapezoidal, whatever shape you've got. If you have a wide channel, then things become a little bit easier. What you can do if the channel is wide is you can use the normal depth and the critical depth rather than having to directly calculate the slope of the energy grade line and the Froude number. A wide section is one where the width is more than 20 times greater the depth. And what that essentially means, the implication of a wide channel, is that it's so wide that the edge effects can be neglected. Even if it's rectangular, if it's trapezoidal, a wide channel is so wide that the majority of the resistance will be along the bottom of the channel, and whatever resistance you get on the side of the channel can be neglected. That's kind of what we're doing with the wide assumption. So this is the process equation. this dy dl. Sometimes in the book it'll talk about the process equation, and this is the one it means. So the sign of it indicates whether the water's getting deeper or getting shallower. And that's really important at being able to classify the water surface profile into the correct category. And we'll look at some more additional pictures of different physical features that cause gradually varying flow, and we'll show how dy dl can be used as a tool for diagnosing what kind of a water surface profile you've got. One other implication of the wide channel assumption is that the normal depth, there's a simplified way to solve for the normal depth. Normally when we are using Manning's equation and solving for the normal depth, we would, for whatever the shape is, Q equals A to the 5/3, slope to the 1/2, and P to the 2/3. All right, so for whatever the channel is, we would put Y into both the A and the wetted perimeter and try and solve for Y. But if it's a wide channel, then you can just take the flow per unit width, Q, multiply it by the friction factor, N, and divide by the channel slope to the 1/2 power, and then all of that to the 3/5 power. So these are some simplifications if the channel is wide. All right, so here is an example that we're going to work through. We have a rectangular channel which is carrying 20 cubic meters per second, and it's 40 meters wide and 2 meters deep. And so that does meet the threshold of it's a wide channel. So we can use these shortcuts. What we need to do, here's the bed slope is given, it's 0.00015, and that's downhill. And we have the Manning's roughness, N. So we want to find out the rate of flow depth variation. So that is dy dl. And then from that, identify whether the depth is increasing or decreasing. And then finally, find the water surface slope with respect to horizontal. So that means combine the channel slope and dy dl and solve for SW. Okay, so I'm going to pause the recording and circulate around as you're working on this. If you want to check some of your intermediate calculations, I'll be happy to show that to you. So we're calculating the critical depth and the normal depth. And you'll do that a lot over the next couple of weeks because we're always interested in how does the depth at a certain location compare to the critical and how does it compare to the normal depth. Now in the past you already knew what it means when the normal depth is greater than the critical depth, or if the critical depth is more than the normal. Remember that that can tell us if the conditions are supercritical or subcritical. Get into that in just a minute. But so if you substitute in the given depths, the normal depth relative to the depth at our certain location, which is 2, this is just at a certain spot we're trying to find dy dl. And so then the critical depth relative to that depth at that certain spot. That tells us the dy dl is 1.39 times 10 to the minus 4th. Now, the interpretation of that is that the flow depth is increasing in the direction of flow. And every 1,000 meters, the water depth would be increasing at 0.139 meters. And that's relative to the channel bed so far. It's not until part C that we're finding out relative to horizontal how things are getting different. So the dy dl is just saying, relative to the bottom of the channel, Is the depth increasing or decreasing? Now, here on the board and also on the screen, I've drawn some dashed lines to indicate here is the critical depth, here's the normal depth, and then our actual flow depth that we're encountering is above both of those. And this is an M1 profile. That M means mild, and anytime you have the normal depth greater than the critical depth, that's a mild slope. It means that the flow is going to be subcritical. Now, zone 1 is the region that's above the first of these lines. Zone 2 is between them, and zone 3 is from the channel bottom up to the first of the lines. And so sometimes, like if it's a steep slope, then it would be the critical depth that is deeper than the normal depth. But here it's mild. And so our conditions are M1 because the water surface itself is in zone 1 up here, and M mild because the normal depth is greater than critical. So there's like a lot of reasoning that you need to be sure to include in your assignments and in the exam, the final exam. You'll need to, explain, not just it is M1, but, show that you know the rationale for why it's an M1. So it would be M2, yes. If the depth was 0.8, then it would be M2. All right, so now part C here. So we've got some dy/dl that we calculated, and then this is where we need to be sure that we account for the negative sign of the slope. So the water surface is going to be actually, it's getting deeper, but the downhill slope is steeper than the rate that it's getting deeper. So the net effect is that it's actually losing, the water surface is losing elevation in the direction of flow relative to horizontal. So my sketch doesn't really show that because we've just got, here's the channel bottom, but what it means is if we were keeping track of, it's getting deeper in the direction of flow, but it's getting deeper more slowly than we're losing elevation in the channel bottom. So like the absolute elevation of the water is decreasing. I guess that's why it's flowing from left to right. You can actually have an adverse slope. Sometimes the water flows uphill. Anybody ever been to a water park where you actually went uphill? I have. It was great. Had a ball. Abu Dhabi. Yeah. Water flows uphill when you've got enough money. Yeah. All right. Any questions on this example? All right. So remember, there are 3 important depths that we're going to be using to classify a water surface profile. The normal depth, the critical, and then whatever is the given depth at a certain location that's been measured and reported in the problem statement. And designating whether it's M1, M2, M3, those sorts of classifications can be helpful to try and figure out what's causing the observed behavior. So even if you don't know what's downstream, the simple fact that you have an M1 profile would tell you there's probably an obstruction downstream that's causing pooling where you're at. And it also helps you to predict as you continue in a certain direction whether it's going to be getting deeper or shallower. So a mild slope is any time the normal depth is greater than the critical depth. And steep is the reverse of that. When you have the normal depth less than the critical depth, that's indication of steep. Of course, critical is when they're equal. Horizontal is when there's no slope. And then here's an adverse slope where the water is forced to flow uphill briefly. Now just the variable definitions sometimes can be confusing. Here they're using y naught to mean normal depth, and previously we've sometimes called that y sub n. But the critical depth, fortunately that doesn't change. But what you need to do to classify whether you have, your first one is M, S, C, H, or A, is just comparing the normal depth to the critical depth. And so, when I say explain the logic behind your water surface profile designation, the first thing is just comparing those. Then the next step is the zone that you're in. Zone 1 is above the highest line, and by the way, sometimes the highest line will be the normal depth, and sometimes the highest line will be the critical depth. But it's still, regardless of which one's on top and which one's on bottom, it still divides this region up into 3 zones: Zone 1, Zone 2, and Zone 3. Okay, Zone 1 is above the normal depth and critical. In this case, if it's a mild slope, then the normal depth would be on top. Zone 2 is between them, and then Zone 3 is below both of them. All right, so if the dy dl is positive, then that means that the depth is increasing relative to the channel bottom. Dy dl negative means that the water depth is decreasing in the direction of flow. Dy dl of 0 just means that you have uniform flow. That is, the depth isn't changing in the direction of flow. And then if you had a free overfall, the water is just flowing over the side of a hill, but then you temporarily would have a dy dl of negative infinity. Okay, so here are some pictures of the shapes as the water is in a different zone. So here, if the slope is mild, meaning less than the critical slope, if the water is in Zone 3, the water depth has to be increasing. It'll always be increasing in the direction of flow. Anybody know of a physical feature that causes an M3 profile? Go ahead.
Eddy.
An eddy? Maybe. Think about an engineered structure, something that you could put into the channel or something you could build that would cause an M3 profile. So M3 means normally it would be flowing subcritical because this is a subcritical slope, but now here the water is in the supercritical zone. If your depth is below the critical depth, that means right now the flow is supercritical, and it shouldn't be. So what causes that? An underflow gate, right. All right, an M2 profile. Anybody think of a physical feature that would cause an M2 profile? So the water depth is decreasing in the direction of flow.
Waterfall.
The waterfall, yep. And what about an M1 profile? So upstream of an underflow gate. So an M3 would be downstream of the underflow gate after the water has actually gone under the gate. An M1 would be upstream of it as the water's pooling to gain energy. It could also be any other kind of a choke. For example, a broad-crested weir could cause an M1 profile. So here are some S profiles. Now it's a little bit different when you've got an S1 instead of an M1. You can see that an M1 is gradually becoming steeper in the direction of flow, but an S1 is gradually becoming, the slope is tapering off. And so whatever the feature is upstream rather than downstream that's causing the change. There isn't a C2 profile, and so you won't have the, because in a critical profile, the normal depth is equal to the critical depth. And so there can only be, the water depth is either above the line or below the line, because both of those lines are on top of each other. So that's why there's no C2 profile when the slope itself is critical. And the same thing is true in the case of a horizontal. There isn't a normal depth. If you've got no slope, you can't solve Manning's equation for some depth if the slope is 0. You can have the critical depth just based on the flow rate and based on the channel geometry, but you won't be able to solve for a Manning's depth. And then an adverse profile, when the water is flowing uphill temporarily, it can be an A3 profile, meaning that it's getting deeper, an A2 meaning it's getting shallower. But again, there's no normal depth for uphill flow. So that's why we only see a single line in both the horizontal and adverse slopes. All right, so an M1 profile could be caused by any kind of an obstruction. This is like a dam of some sort, like a spillway, and the water's going over the spillway at a critical depth. Here's the flow over a drop-off, hydraulic jump. So before the hydraulic jump is gradual flow as you've got supercritical conditions, and it's gradually increasing until it matches the sequent of the normal depth downstream. So those are some things that can cause mild slopes. Here are some features that can cause steep slopes. So here we've got a supercritical slope, a normal depth, and then it has to go through a hydraulic jump to match up with the S1 because it's going to be temporarily, the normal depth should be below the critical depth, but this is going to be forcing the flow depth to be greater than the critical depth, and so it has to go through that hydraulic jump to match it. These are in the book, pictures like this, and so if you have a problem where you're asked to draw, I think you do have a homework, where you're asked to draw, like after a gate, what would the profiles look like? Then it can kind of give you an idea of like the typical shapes of the water surface. Here are some hypothetical situations that could cause an A2 and an A3 slope. Or if the slope itself is critical, what could cause a C1 and a C3. This is just another book's way of showing it, and I like this because it's got in the same diagram, it shows you dy dx is positive. So you can use this to help you analyze whether it's an M1, an M2, or an M3. So what you're doing is you're comparing the given depth to the normal versus the critical, and so then that will tell you if the dy dx should be positive or negative. And comparing the normal depth to the critical depth will tell you if it should be a mild slope or a steep slope. And this is what we'll have most of the time, is an M and an S. These other ones are far less common, very unlikely to have a horizontal slope or an adverse slope or critical. Here they are, but they don't happen very frequently. Okay, so we have time for one more. 9 minutes. No, we don't have enough time. I don't want to rush this one. So be sure to bring your computers to class next time. And okay, so here are our announcements. Homework assignment due on Thursday. The project due a week from today. A few key ideas for the homework assignment. Let me know if you need any help on the homework. I've got office hours tomorrow and on Thursday. I guess the ones on Thursday still are before class, but anyways, have a good day. I'll see you Thursday.